Hello and welcome to the YouTube channel D Creations Resources. Today we are going to talk about an experiment called measurement of magnetic susceptibility by Guoy's method. This particular method works on a simple principle that a magnetic body experiences a force when placed in an inhomogeneous or non-uniform magnetic field. So in this experiment, it is very important to have a field gradient. We use an electromagnet in this experiment, and if a material or the sample which is attracted by a magnetic field is to be tested, such a sample is going to appear heavier when placed between the poles of an electromagnet, while if it is a material which is repelled by the magnetic field, it is going to appear lighter. Or in simple terms, if we have a paramagnetic sample which is attracted towards the external magnetic field, then there is going to be an increase in the weight, while if the sample is diamagnetic, there is going to be a decrease in the weight. Now, in order to understand the importance of non-uniformity of field, let me give you an analogy. So, imagine that a uniform field is like a flat region, flat plateau kind of a region. Now, if you have a ball and if you keep it there, will it roll? No, it will not, because the region is flat. But if you keep the same ball on a slope of a mountain or a hill, then it is going to roll. So there's a slope, that means it is inhomogeneous, it is non-uniform. So there the ball will roll down to the region of lower potential energy. Now again, if you come back to magnetism, for a paramagnet, the region of stronger field is going to be of lower potential energy. Now we have a separate episode on magnetic susceptibility, but here I would just mention that it is a fundamental physical property that describes how a material responds to an external magnetic field, or how magnetizable is the substance, right? In simple terms of a formula, we say M is equal to chi into H, where chi is the magnetic susceptibility, or you can rearrange it and say that chi is equal to M, capital M by capital H. Now what is capital M? It is the magnetization. That is, it is the magnetic moment per unit volume of the material. So that basically tells you how strong the induced magnetic field within the material is. While capital H is the magnetic field strength. It is the strength of the external magnetic field which is applied to the material. Now, paramagnetism is caused by the presence of unpaired electrons in the material's atoms or ions. And these electron spins basically act like tiny magnets that align with the external field. So there's a net attraction. That's why paramagnetic materials have a positive susceptibility. That means chi is greater than 0. While when it comes to diamagnetism, it's a fundamental property of all matter, and it arises from the motion of paired electrons in atomic orbitals. So when placed in a magnetic field, these electrons generate a weak opposing field, causing a net repulsion. So diamagnetic materials have a negative susceptibility. That means chi is less than 0. Now in this experiment, if you have MnSO4, manganese sulfate, as the sample, it is paramagnetic, and the capillary that you are using for filling this sample is made up of glass, which is diamagnetic. So what is going to be the experimental setup? Well, it would need a strong electromagnet which is designed to produce a very strong magnetic field that is highly non-uniform. This field is strongest in the gap between the pole pieces, and it is going to drop off rapidly with distance. Then you also need an analytical balance, a very sensitive balance which is capable of measuring changes in weight, and the changes in weight can also be of the order of milligrams or even micrograms. So for example, you can have a balance whose least count is 10 microgram, that is 10 raised to minus 5 gram. And then of course you need a sample tube, a long thin cylindrical tube which is made up of non-magnetic material or basically diamagnetic material like glass, and it is suspended vertically from the balance. Now it has to be suspended in such a way that the bottom of the sample tube is in the strong magnetic field while the top of the tube is in the region where the magnetic field is negligible, finally even becoming effectively zero. Now many times in the first part calibration of magnetic field versus current is done, and after that the procedure involves preparation of the sample. Now it could be mostly in a finely powdered solid form, and it is packed uniformly into the sample tube. The weight of the empty tube is recorded, and then the length of the sample column and is also noted down. Now initially when the magnetic field is off, it is going to show some value of weight. Now with the electromagnet turned on, this value is going to change. For a paramagnetic sample, there will be an increase in the apparent weight. But initially, if you consider an empty tube which is diamagnetic, it is going to show a decrease in apparent weight. Now the change in the balance reading is recorded, and this apparent change in weight is directly proportional to the magnetic force which is acting on the sample. To summarize, in this historical method proposed by Guoy in 1889, magnetic susceptibility is measured by determining the force on a sample when the sample is placed in a non-uniform magnetic field provided by an electromagnet, and the sample is placed in a long cylindrical tube which is suspended from a balance in such a manner that its one end is in the strongest part of the field and the other is outside of it. And the apparent change in the weight is measured as the field is applied and is varied. So chi is 2 delta mg upon mu naught h square L, where delta m of course is the change in the weight, and g is going to be the acceleration due to gravity, mu 0 is the permeability of free space, capital H is the magnetic field strength, and L is the length of the sample. So if you plot a graph of delta m versus h square, you can find its slope and then you can plug that value into this formula to determine the magnetic susceptibility.